It's very happy to be here. So first of all, if there are some things you don't understand related to the language, please raise your hand and you can ask me to repeat and try to explain things a little in a different way. And same thing goes for math. There's not going to be a lot of math in this class, but especially today, I'll do some calculations, and I don't want you to get lost in the details of a mathematical derivation, and then you miss the basic concept. So please don't be afraid to ask questions. And yeah, so I'll be here all week, and so if you can find me and after class if you need to discuss things in more detail. And also, I'm thinking of having, I don't know how you're used to when you have 2 hours classes, but I would like to have like a 5-minute break after 1 hour, if that's fine with you. So, and I don't see any watch here, so maybe I'm gonna need to ask you to like let me know when we're close to the 1 hour mark and all stuff. So, thank you. So this is a class on observational astronomy. So I'm an observer. I work mostly on galaxies, and so what observers do is try to go from data, where data can be a lot of things. It can be images, can be spectra, it can be time series, so combinations of either images or spectra in time. And we're trying to go from there to some physical understanding of reality, of the universe. So this class is meant to be an introduction on how to best go from data to a physical understanding. And this process, very generally, can be summarized in 3 steps. So the first step is the modeling step, where and it's also the most difficult step, where we sit down and we try to summarize physical reality with a model. And a model consists typically of some parameters. So it's a huge reduction in complexity, going from reality, which is extremely complex, to a few parameters. And this is the hardest part of the work of an observational astronomer. And this is where the physics is in. So, and it's also the most fun part, in my opinion. So assuming we have a model, then the second step is the inference, which is commonly referred to as fitting a model to the data, but I like to call it inference. But yeah, it's basically we're going from data to some quantification of the possible values of the model parameters. So, and there's different ways to go about doing this. And this class is going to be about Bayesian inference. And I'll get to, in a minute, I'll explain what it is, but just as an introduction, I should say there are 2 fundamentally distinct ways of doing inference. One is Bayesian statistics, and one is frequentist statistics. Now, the Bayesian formalism was the first one to be developed, but with the years, frequent these approaches became a lot more common, especially in the last century and especially in fields like particle physics. So yeah, this is a warning. Like even nowadays, most people don't rely on Bayesian methods to do this step. So you might be wondering then why are we learning this if it's not the most widely adopted method? Well, because there are some things that Bayesian statistics makes a lot easier, especially the modeling part. So yeah, so the goal of this course is to let you appreciate how using particular methods for step 2 can also help with step 1. This will all be clear once the course goes on and you'll see some examples. But yeah, so this is only the second step, and then the third step is, I call it the prediction or the check step of the model. This is when you made an inference, so you fitted the model to the data. Now you have a model with some parameters, but the work of an astronomer doesn't end there. You need to critically assess the meaning of the model. So one way to do this is to make predictions. So now you have the model, and you can use it to predict. You can use it to predict literally future events in some cases. One beautiful example of prediction based on a Bayesian model in astronomy happened a couple of years ago when there was a supernova exploding behind the galaxy cluster. And the supernova was strongly lensed. So gravitational lensing is a phenomenon where you can have multiple images of the same object in the sky just because so this is us, we're observing. This is a massive galaxy. And this is a supernova. Because of gravity, the light coming from the supernova, instead of going in a straight line, it goes like this. So you could have two different images of the same object in the sky. The case I'm talking about it was behind the galaxy cluster. So what happened was that we had 4 images of the same supernova appearing, and then fading away because the supernova is a transient phenomenon. And based on the model for this gravitational lens, the people who studied it were able to predict that in a few months there was going to be a 5th image appearing somewhere else in the sky. And in fact, it happened. So there was a paper saying we predict that by December 2015 there's going to be a 5th image, and that's what happened. So this is an example of application of this step, which is very important because it gives credibility to your model. Unfortunately, this is an exception. In astronomy, we in most cases we don't have the luxury to make a prediction and then see it happen, but this is one example. And then I also wrote check. What I mean here is that your inference is only going to be as good as your model. And your model is going to be good at predicting some quantities, but maybe it will make it won't make much sense for other quantities. So it's always good to check the reliability of the model. One example is if your model predicts, you write down a model, you feed it to data, you get some numbers. If one of these numbers represents the mass of a galaxy or of a star, and you find a negative value for that mass, then maybe you should ask yourself some question. It means the model is not totally accurate. So it's always good to think critically about what we're doing. All right, so this was a brief introduction to what we're going to do. So today, I'm going to introduce the basic concept of Bayesian statistics, and then we'll do some problems on how to infer parameters on a class of problems in a one-dimensional space. So all the problems we'll see today will have one parameter, and we'll have some data, and we'll try to make an inference on the value of that one parameter. Tomorrow we'll start generalizing this approach to model with more than one parameters, and we're gonna do also some. If there's time, I'm going to introduce tomorrow the concept of hierarchical inference, which is one of the most powerful uses of Bayesian statistics. And then we'll see from there, based on how quickly we make progress. All right, so why is it called Bayesian statistics? Well, the basic concept of this method were written down by Reverend Bayes, who lived in the 18th century. And then the basic concepts were elaborated by Laplace. But everything is based on the rule of conditional probability. So I'm going to use this whiteboard for expressions that are going to be there for the whole week. And I'll be erasing this one. So the main concept over which all this is based is this rule of conditional probability. So P always indicates probability. Here I'm writing the probability of A and B, where A and B might be two events, is the probability of A given B times the probability of B. Does this make sense? So this can be derived from some axioms, but I think this intuitively should make sense. So if I want A and B to happen together, the probability of that happening is equal to the probability of B happening times the probability of A knowing that B happened. But this is also equal to P of, the problem is symmetric to permutation of A with B. So I can also write it like this. Or I can rearrange terms and write the probability of A given B is equal to the probability of B given A times P of B. And of course, I made a mistake. Now, why do we need this? In practice, as far as we're concerned, we're going to use this in the following way. We're going to be asking, if we have a model and we have some parameters. So I'm going to indicate that with theta. So it could be, I don't know, the mass of a galaxy. D is the data, for example, the luminosity of the galaxy. And we're going to be asking what is the probability of the parameter having a specific value theta given the data that is equal to the probability of the data given the parameters times this times that. Okay, so probably this also doesn't tell you much, but hopefully you'll see how this is used. So why don't we just start with an example? So the first example I'm going to use is not based on astronomy, but it's based on biology, and it's from a book, Bayesian Data Analysis, from Gell-Mann et al. And it's based on, it's the following problem. It's based on a disease called hemophilia. So it's, so this is a genetic disease that's related to some blood clotting problem. Anyway, so it's a genetic disease. It's related to the X chromosome. So males and female so males have an X and Y chromosome, females have double 2X chromosomes, and this disease is related to a defective gene in the X chromosome. So, I don't know, we call it X star. And it's a recessive disease, which means if, for a man carrying this chromosome with the bad gene, it shows symptoms. But a woman with only one gene, one chromosome affected, it doesn't have it doesn't show any symptoms. So and now I have to consult my notes because I don't want to make any mistakes. So the problem is the following. We have a woman with a brother who's affected by this disease. So a woman with an affected brother. An affected brother means that the man always gets the X chromosome from the mother. So we know that their mother must have one of the chromosomes must have the bad gene. So there's a 50% chance that the woman is carrying the bad gene. Does that make sense? Right. So let's write. So that's the starting point. Then what we know is that she has two sons, and neither of these sons is affected. So let's write it down. Let's write the problem down using that notation. So the data here is two sons not affected. The parameter is the following. The parameter is she's carrying the bad gene or not. So there's two possibilities. I'm going to label them like as 1 and 0, which means has the bad gene. Or does not. Are there any questions? So we'll be asking, what is the probability of a specific value of theta, which could be 1 or 0, given that we know that she has 2 healthy sons, and according to the rule of Bayes' rule, this is the probability of observing the data, probability of having 2 sons unaffected, given the specific value of theta, times P of theta divided by this. Now, what is this? This is just the probability of a particular value of theta independently of the data. This is called the prior probability. This is the probability that we assign to a specific value of theta before we carry out the experiment, or before we look at the data, or so it's our original knowledge about the situation. And in this case, I think you can be convinced that a good value of P of theta is 1/2, because of the argument I made earlier about, because we know that the woman has a brother who's carrying the gene. But in general, assigning this P of theta is not that straightforward. So actually, a more general way of writing down this problem would be this. So there's not only the data, but there's also an initial knowledge. When we look at a problem, experiments don't happen in a vacuum. We usually know something about the experiment before we carry out the measurement. So, and here I'm indicating as I as the initial knowledge about the system, which for this problem would be what I wrote here. So really, what we're doing is inferring the probability of the data given theta and given our knowledge. And then this becomes the probability of theta, the prior probability given our initial knowledge. So I've talked about this term. This is called the likelihood. So this is called the prior. And this is a probability of observing the data. In most cases, this is a normalization constant. But so let's not worry about that now. So I'm gonna go ahead and erase this. So the original question is, what was the probability of theta being 1, that is, she has the gene, given the data? So I'm going to use that. And to calculate that, I need to first calculate the likelihood. Now, this reads, if she has the gene, what's the probability that both her 2 sons are healthy? So for one healthy son, so she has a, so we are in this situation, so she has a 50% chance of giving the bad gene to one of their sons. So there's a 50% chance that the son would be healthy. This is for 1. There's 2 sons, so the probability becomes 1/4, right? And then we have said that the prior knowledge of theta being 1 is 1/2. So now we have to calculate this term. So this is the probability of observing the data obtained by marginalizing over all possible values of theta. I'm going to be using this term a lot, marginalizing. It just means summing over all possible values of theta, which in this case is only 2, but right? So whatever the value of theta is, what is the probability of observing this data? So you see that now I need to compute one more term, one more likelihood term. So, sorry, let me move this down here. So earlier we calculated what's the probability of having 2 healthy sons given that she carries the gene. Now this is what's the probability of having 2 healthy sons given that she does not carry the gene. And if we also know that the father doesn't have the bad gene, which let's assume that we do, this is no? Any guesses? 1/4? No. If she's healthy, what's the probability that both of her sons are healthy? 1. So yeah, let's put everything here. And let's see. So we've got the first term is 1 times 1/2 plus 1/4 times 1/2, which is 5/8. This. So remember we calculated this to evaluate this quantity. So now we can put everything here and write 1/4 times 1/2 divided by 5/8, which is 1/5, 20%. So this is our answer. So we know that there's a 20% probability that she's affected. So that's pretty nice, I think. Any questions?
Teacher, what the I means in the part? The I.
Here?
No.
The I.
The capital I.
It stands for initial knowledge of the problem. So everything we know about this before we collect the data. For instance, in this case, well, what the disease is, how does it work, and then what I wrote here, like the fact that she has an affected brother. In general, in astronomy, this could be, well, all of our physical knowledge about the system. Other measurements that I might have carried out before these new measurements come in. In fact, I'm going to just show you an example of this. So suppose we add more data. Suppose she has a third sun, and the third sun is also not affected. We could do the problem again from scratch and use change the value of d, or we could use what we just learned about the situation from this problem based on the first two data points and use that as a prior for the new problem. So now I'm going to change this. So third sun also not affected, and so the situation here changes because now we know. So in our initial knowledge, we know this, but also first two suns healthy. And now I have to change the prior here. So based on the first two suns, we know that there was a 0.8 probability that she's healthy, 0.2 probability that she's carrying the disease, and we can ask that question again. So this, with the new data, this is 1/2 because there's only one new sun. This is still 1. If she's healthy, the sun is healthy for sure. Well, and this still applies, but this becomes 1 times 1/5. 1 times 4/5 plus 1/2 times 1/5. And I have to, so this becomes 1/10, 8/10, 9/10. And here we've got, let's see, this term, 1/2 times the prior, 1/5 divided by 9/10, which is 1/9. And so you can see for exercise, if you want, I can leave it as an exercise to demonstrate that you get the same result if you started from the top, knowing that she has 3 suns unaffected. Any questions? No? All right, so let's move on. So this is, well, I guess you didn't come here to learn about genetics, also because I don't know anything about that. So let's move on and let's start introducing continuous distributions. So this is a discrete problem. So the parameter of interest can only take 2 values. But in general, in astronomy, we're dealing with continuous distributions. So, right, let me write down a few basic equations that we're going to use. So we're going to, all of our probability distributions, if theta now is a continuous variable, well, even if not, but They all have to be positive defined for every possible value of theta. This makes sense. Negative probability doesn't make any sense. They have to be normalized to unity. So if I sum over all possible values of the parameter, I have to find a probability of 1. That is, the probability of the parameter having any value is 1. And the same if the model is discrete. So, well, let's just leave it like here, like this. But if you sum over all possible values of the parameter theta, you must find 1. A few other quantities that I'm going to use often is the expectation value of a quantity of a function h of theta is defined as the integral of h times p. For example, in case, so for h equal theta, this becomes expectation value of theta becomes this. So this is what we're doing here is we are weighting. It's an average. We're weighting theta by the probability of theta having that value. So we're in this case, this is the mean. And also a commonly used quantity is the variance, which is defined as the expectation value of theta. I have to look at the notes. Which, well, I saved you the algebra, but becomes this. I'm just introducing quantities that I'm going to be using later. They don't necessarily mean anything physical, but they're useful to describe probability distributions. These are summary quantities. So a probability distribution can be complicated, but if you just want to get an idea of how it looks like, this is an arbitrary probability distribution, but if I tell you that the mean is around here and the square root of the variance is like this, you more or less get an idea of what this distribution looks like. And let me just erase this ugly thing. So again, no concept here, it's just definitions. Yes?
Could you please repeat, or I didn't really understand what the h stands for.
It's some arbitrary function. We don't really need
Analog of the data for the discrete problem, or?
no, for example, so here I should have written h of theta equals theta, then you get this. But you could say h of theta equals theta squared, and then
Is it like an arbitrary function or it could have a meaning eventually?
Yeah, we're going to use it in cases where this quantity tells us something. So, for example, theta squared. So the meaning of this is a good way of telling what's the mean, the width of the distribution. So since theta squared is always positive, by taking these expectation values, you sort of get a measurement of how the data is dispersed. I'll show you an example. So the first distribution that we'll look at is going to be the Gaussian distribution, which is the following. So if a quantity y is distributed as a Gaussian is described by two parameters, the mean and the variance, and this is and it looks like this. So it peaks at the value mu, and also the expectation value of y. One can derive that is mu, so the mean value of this variable is mu, which can be interpreted as if I have this distribution and I draw random numbers from it, and then I take the mean. In the limit of a large numbers, I expect to find this value. This is it's a frequentist interpretation of the mean, and also the variance is sigma squared, and right, and also it might be useful to know that the weight of this distribution, so the full width, a half maximum means if I take the point here where it's half of the height, and I measure the width of the distribution, this is 2.35 times this parameter sigma, which is also called the dispersion. It's just an intuitive way of visualizing how these parameters affect this distribution. So if you change mu, you shift the distribution. If you change sigma, you make the distribution broader. And since we have to satisfy this condition, the probability must always be normalized to 1. If you make the distribution broader, you also need to squish it. So that's why there's a sigma at the denominator to make sure that when you take the integral, it integrates to 1. Now this is a very useful distribution for two reasons. One, because it makes computations very easy. So in the next few days, a lot of the problems that I'm going to use will be based on the Gaussian distribution. But there's also a more profound reason that is, which is roughly based on the the large numbers laws, and that's when you have a lot of when you have when you have a process to which contribute many independent measurements or processes in the limit of large numbers, that the resulting probability distribution is a Gaussian. So this is very roughly why we're going to use a lot of times this distribution. So let's see a problem based on this distribution. So suppose we have a sample of data points, which could be a number of independent measurements of the flux of a star. Strictly speaking, the use of a Gaussian distribution is not correct for this problem, but in the limit of large counts, we can, right, in the limit of large counts, a lot of distribution converge to a Gaussian. So I guess I can erase this. Okay, I just said let's take n different measurements, but before, let's start with only one measurement. So suppose we draw one value from a distribution describing a physical system, for instance, the flux of a star that we approximate as Gaussian, the distribution of counts from a star. And suppose we take one measurement only. So we draw a value of y, and we want to know, and suppose we know the value of sigma, which in a lot of cases this represents the uncertainty in our model. So suppose we know sigma, and we want to ask what's the probability of having value mu, of the distribution having value mu given the data. So again, I should write this is the likelihood of observing that single value of y given mu times the prior, and this is the probability of the data. Now, we can also forget about this and just write this. Since in many cases we're not really interested in the absolute value of the posterior, but only the relative values. We want to know how different values of mu are more likely with respect to each other. Does this make sense? Do you know this symbol? Okay, proportional to? Yeah, okay. Good, so now in the previous problem, remember we had to assign the prior probability to our parameter. And we did that based on the fact that we knew the brother of the woman is affected, but yeah. So in this problem is how do we assign this prior? So this is we're often in a situation like this where there's no obvious way to assign a prior probability on this. And this will affect our answer. So depending on different choices we make for this, we will get different answers. And this is oftentimes the main criticism that people who don't use Bayesian statistics move to this method, because they say, well, what does it mean that your answer depends on your choice for the prior? It's not scientific, but well, we'll see that in the end, if the data, well, first of all, if the data dominates, if the data is really informative, then it doesn't really matter much what prior he assumes. And two, it's actually a good thing that the person who does the inference puts, this gives you an ability to put any knowledge you have on this into the measurement, and it's a good thing. I see it as a way of giving the researcher the responsibility of putting your ideas into your inference. Okay, maybe I didn't explain that very well, but I hope in the next days this will become more clear. Okay, so for the sake of this exercise, we're going to assume that we're going to take a prior that is also a Gaussian. And I'm going to use this notation a lot, exponential, instead of writing this. Do you know what? Yeah. All right. Let's. I wanted to change variable because I started everything using theta, and now I switched to mu. But since I already started writing notes using mu, I'll stick to mu. And so this, I call it mu p. P stands for prior. All right, so it's a Gaussian prior. It might not make much sense, but maybe we know we have a broad knowledge of what the expected value of mu p is. Anyway, let's see how much this impacts our results. So we want to evaluate this, and so this is it's the product of two Gaussians. Sorry about that. Okay, we've got the product of two Gaussians. So one way to address the problem is to stop here and plot this function. We are interested in this as a function of mu. So this is the probability distribution of mu given everything else. But in this case, it turns out we can further simplify this expression, and I'm not going to do that in the interest of time, but it can be shown that this is proportional. The product of Gaussian is proportional to a Gaussian. And so the way to see this is we've got, so first of all, the terms in front, they're just constant as far as we're concerned. So everything that matters is in these exponentials. But we've got two second order polynomial in mu, and you can always rearrange the terms to make it to rewrite it as something like this. Does this make sense? you can rearrange the coefficients to write this in this form. I just call this sigma 1 for a reason I'll come to soon. And this since we're only caring about terms that depend on mu, everything else is a constant for us. And this is mu minus mu1 squared. So our posterior probability distribution, so this, by the way, is called the posterior probability distribution. I didn't say that, but posterior probability distribution of the parameter given the data. And that's what we're going to be doing for a large part of this week, is proportional to a Gaussian in mu. So we had two Gaussian terms. The product becomes a Gaussian. Now, what are these mu1 and sigma 1? They are let's see. Okay, what is this? So the new mean of this Gaussian distribution, which I'm gonna, well, okay, this is easy. Just add the one here. So the posterior probability distribution looks like this. And the new mean is a weighted mean between the value y that we drew from the Gaussian and the mean of the prior. So it's a compromise between our prior knowledge of what the value should be and the value that we observed. And the relative importance of these two terms depends on the width of the distribution. So if tau is very large, this term doesn't really matter. So in the limit where tau goes to infinity, our prior distribution is a flat distribution. That is, it weighs equally any possible value of mu, and all that matters is the observed data. On the other hand, if sigma is large compared to tau, it means that the data is not very informative, and in this case, the answer will be close to the prior. So this is the new mean, and this is the new dispersion. Sorry, this is the variance actually. And it can be shown that this is actually smaller than the original value. So the fact that we added the prior sort of shrinks the distribution, or the data shrinks the distribution of the prior. Oh, it's also smaller than theta 0. Are there any questions? If not, I'll move on to the more realistic result when we actually have not only one data point, but many. And so, yeah, I'm gonna use this blackboard again. So, let's see. Now we draw not just one value of y, but we draw a set of n measurements from the same distribution. Again, we know the value of theta. Again, we assume this prior, and then what happens? Well, if the draws are independent, now we're asking. So our y is really, I rename y as this collection of measurements for simplicity, so I can leave everything as it was. But now this is not just one of these terms, but is as many as, it's as many terms as data points, so this becomes so I'm cheating, sorry. I apologize because I can't do this, you can't on your notes, but hopefully it won't be too much of a problem. So now, do you know this symbol? It's the product of n terms, one per observable. So, and then we have the prior. But to avoid confusion, let me rewrite this from the top. Sorry. So this is, let's write the prior first. All right, so we have, this is n Gaussians times 1 Gaussian in mu. Again, everything can be rearranged, and it can be shown that the product of an arbitrary number of Gaussians is proportional to a Gaussian. You can look for the demonstration online. If you just Google product of Gaussians, you'll find all of these expression. And but what matters to us is that, yeah, the mean of this product of Gaussians is this. The y bar is the mean value of y. It's the average on the data points. So now, a very important difference with respect to earlier is this n term. So as the number of data points becomes larger and larger, it doesn't really matter what the value of theta 0 is, or what the prior is, because this term will dominate. So as n becomes very large, the prior loses importance, and what matters is the data. And the same thing happens for the dispersion, which is this. So as n goes to infinity, this becomes sigma squared over n. Now, why do we care about this quantity? this sigma n is, so what we're looking at, this distribution here, is the posterior probability distribution of the mean mu given the data. So is our answer to the question, what is the value of mu? And I said that the answer is proportional to a Gaussian, and this is the sketch of a Gaussian. And the width of this Gaussian is proportional to sigma. In this case, sigma n. As n becomes very large, our sigma becomes smaller and smaller, which means that this distribution is going to become narrower and narrower. And what does that mean? It means that our answer is better and better constrained. So when we only had one data point, we had a distribution that was broad, which means, for example, we gave a certain probability. Well, we didn't constrain much the range of the parameter values, and I'll tell you later a few ways to do that we can use to constrain the values of parameter. But I think you can see that as this value becomes smaller and smaller, our inference on mu becomes more and more precise. Are there any questions? Okay, we're gonna take a 5-minute break, and so. So let me summarize what we're trying to do here. So for this problem that we just looked at, the situation is the following. We have, some process that generates data, y, and we think we can model that. We have reasons to model that as a Gaussian distribution. Let's just believe that. Let's just assume that. And so, let's also assume that we know what the variance of the distribution, or the dispersion, or the scatter. I'm going to use these terms interchangeably, but what I mean is the parameter sigma of that distribution is. And we're saying that there is a true value of mu from which the data are generated. And what we're trying to do is to infer that the true value of mu given our limited observations. And our answer to that question is this. It's a probability distribution, which, if we draw it, is here. But a lot of times what people need is not if you ask you what's the value of mu, I can give you a probability distribution that you can plot, but it's not a very useful way to summarize our knowledge. So a lot of times we use different summary quantities to summarize the results. So, and I'm going to go through them here. So suppose we have a probability distribution that with some arbitrary form, like this. Sorry. Let's start from an easier case, because this can be a bit annoying to deal with many peaks. So one way to summarize this is with the mean. So you could take the mean, and the mean is the mean is the expectation value of theta. Times theta. So for our problem, what is the mean? The mean of a Gaussian is the parameter mu. So in that case, is what I call mu n. Let me erase it from here because I don't want, this is a general example, but yeah, well, you know what I mean. Another way of quantifying the typical value of this distribution is the median. So the median is that value of the parameter for which we have this. What is this? It means the sum of all the probability, the sum over all values smaller than the median is equal to the sum, to the probability of the probability of theta having values larger than the median equals to a half. So there's, it means if I draw random, again, a frequentist interpretation of this is if we draw random values of theta from this distribution, I have a 50% chance of picking values below the median or above. So in this case, the area here is equal to the area there. Yes?
You say the frequentist interpretation of that value is that, does that mean that Bayesian interpretation is a different one? Or why do you make that emphasis on that word?
Yeah, well, well, because the whole point of frequency, so the frequentist interpretation is you have you know, a quantity is what you obtained by making an infinite number of experiments, and in Bayesian statistics, the reasoning is not that. We're dealing with the data, which is finite, and we make, and all our probabilities that matter are probabilities of the true value of the parameter being in some range. So it's not like we're drawing, if you apply the frequentist interpretation to Bayesian approach, it would mean that you draw infinite values of the universe where the true parameter is this, and
so, but my question goes towards the median in the Bayesian interpretation is different.
no, okay, the median is this.
Okay.
So this is the definition of median, that's all we're gonna work. The interpretation is, right, so it's, we have, the interpretation is, for example, in this case, the probability distribution is our inference of mu given the data, which means we give equal probability to values of mu below the median than to values of mu above the median. So we, as far as we're concerned, after doing this experiment, we think there's a 50% chance of the true value of mu being below this. So it could be either below or above this value. That's what we mean by, yeah, that's how we interpret probability distributions in Bayesian statistics. So median could give you good estimates of what's the, if you want to summarize that distribution with one number, we could take that, but of course we're scientists, so we want to also give a measurement of the uncertainty to our measurement. So, right, so there's different ways, again, to do that. One quick way is to compute this quantity, the variance of the distribution, and then take the square root. It's not a particularly profound solution. But another approach that I use frequently, at least, is to take quantiles. So I could look, for instance, I'm interested in giving a credible region estimate. So I want to tell you what is the range of values for which there's a 90% chance that the truth lies. So I could give you this. I could define a theta 5 or a theta 95 such that the probability enclosed below this value, and now so the way I've defined it here is the value for which if such that, the area between, the probability enclosed between this point and infinity is, again, 5%, so that what I'm left with is this interval, which means there's, if I give you these two numbers, then I tell you that I think there's a 90% chance of the true value of theta to be in this region. So this is what we do often, but we could also make a different choice. So now, I could give you, for instance, the median and this interval. Or I could give you this interval and that's it. Or one thing that we do, especially when we work in higher dimensions, is we look for the level at which the area is some fraction of the area underneath the points with probability above the level is some fraction above some fraction of the total probability. So a lot of times we use 68%. You might be wondering why 68%, such a random number. 68% is because for a Gaussian distribution, the area, so the probability enclosed, not here, but the probability enclosed within 2 sigma, so with 1 sigma aside from each side, is 68% of the distribution. So when we say the 1 sigma confidence region, the 1 sigma credible region, we mean the region that encloses 68% of the probability. So these are all different ways to summarize as result. Any questions? If not, I'm going to move on to a more physically relevant problem. So the problem is based on supernova explosions. So, and it's something fun that we can do, and then we work also later in the lab. And it's the following. So, in the Milky Way, in the past couple thousand years, there's been a few supernova explosions. And that we know of based on historical records. And based on this data, we can make a prediction of one on what is the average rate of supernova explosions in our galaxy, and two, maybe we can make a prediction for when will the next supernova explosion be. This is a very relevant question for some people. For instance, people working on neutrino experiment, they're hoping to get, if we get a supernova not too close to us, but still within our galaxy, it can be very useful for neutrino physics, because then we can get a lot of neutrino flux. So, but experiments cost millions of dollars or euros, so it's important to know to make these kinds of predictions. So the physical process we're dealing here is of a stochastic nature. It doesn't need to be, because if we have a star and we know everything about the star, and we knew everything about nuclear physics and stellar physics and everything, in principle we should be able to predict when the star will explode. In practice, we don't know that, so our uncertainties on stellar physics are much larger than the typical interval between supernova explosions. So for our purposes, we can treat this situation as a stochastic process. And in that case, when you have a stochastic process for something of which we can take counts of, this is governed by the Poisson distribution. The Poisson distribution so is described by one parameter, the rate. And then so this can be interpreted as the average event rate in some unit of time. And so in a time interval delta t, the probability of observing an event, and I don't want to make stupid mistakes, so I'm gonna look at my notes just to be 100% sure. This is given by okay, so right, so if you know this parameter, the value of this parameter, the rate, and then if you have a time interval, you can ask what's the, this is a discrete probability distribution. You can ask what's the probability of having 0 events in that time, 1 event, 2 events, 3 events. If m becomes large, this becomes very difficult to compute even with a machine, but there are approximations. The other nice thing is that this, for large n, this tends to a Gaussian distribution. Right, so I did a quick search online, and I found that in the past 2,000 years, the number of more or less credible accounts of supernovae in the Milky Way is 9. It's probably more because of incomplete record tracking and blah blah blah, and parts of the Milky Way that are less visible. But let's assume that is our data, and then we can ask. We want to know what's the supernova rate in our galaxy. So we can ask what's the probability of the rate having a specific value given that we've observed the data. And so what did I want? So this is the likelihood. Times the prior. For simplicity, let's take a uniform prior. So the rate must be positive. Doesn't make sense to have a negative rate. So we can take any value between 0 and infinity. Sometimes there are problems if you make this choice. This is an improper prior. It means that it's not normalizable, because if you integrate this distribution from 0 to infinity, you get infinity. But in practice, if the likelihood is sufficiently informative, this doesn't matter. So as long as the posterior is normalized, we can use improper prior distributions. Now, so the likelihood is I take that from that expression. And then, since we're multiplying this by a flat distribution, this is also the posterior in the end. And it's going to be something like this. So later I'm going to have you guys with the computer to compute some of those quantities to summarize this result. So yeah, I will ask you to provide estimates for what are the most likely values of the rate, and plug in the numbers and compute this quantity. So one thing we can do, one thing you'll do is to make an inference on what the supernova rate is in our galaxy. But another thing we can do is once we have this result, we can make a prediction for when the next explosion will be. And I don't really have time to show the derivation, but that is, so probability. So given a Poisson process, the probability of having at least one event in time interval, well, let's see, between t0 and t is this. So given the rate, this is what we get, which is, so this is related to the exponential distribution. But if we were to plot it, yes. It would be something like this. So the probability of having one event or more in a time interval 0 is 0. I think that makes sense. And then if you wait long enough, there's gonna be an event, and then this is why the probability converges to 1. And for instance, the value at which there's a 90% chance of that happening corresponds to roughly 2.30 over the rate. All right, so suppose somebody told you the value of lambda, the rate. Suppose we know that exactly. What we can do, one thing that is a very important aspect of Bayesian statistics is the ability to make predictions. So we can use this model and the value of lambda, which for the moment somebody told us, to predict the probability of having an event. And so this is exactly what I just said. So if we know lambda, this is it. But in general, we will not know the value of lambda. So what do we do? So our knowledge of lambda is not a number, but is a distribution. It's this. So how can we combine this with this model to give a probability of a supernova explosion before time t? Well, we can weight, so we can take the mean of this distribution weighted by the probability of each value of lambda, which in mathematical language becomes this. So we're weighting this distribution times this. Now this, okay, you might be wondering, this is the integral of a function of t. So how do we do it in practice? In practice, we're not going to actually calculate this integral, but a central element to Bayesian inference in practice is the use of simulations with a computer. So, and this is what I'm going to have you do today. So, what we can do to estimate the probability of a next supernova explosion within time t, given our knowledge of the parameter lambda. One way to do it is to do the following. You can draw random values from this distribution. For each value of lambda, then you can go ahead and draw a supernova explosion or more event from this distribution. And then you can just make a plot of, basically you can draw a value of t from here, given lambda. You draw a value of t, and then you can make, you can plot any histogram of that p of t. So for instance, well, yeah. So the result is going to be I don't know. All of my probability distributions look like this, but you'll notice once you start working with actual example that often case, you know, they have a peak and they go to 0 for large values of the parameters, hopefully. Anyway, so I'm going to explain you better later how to actually do this in practice, but one thing I want to cover, and do we have time? Yeah, 10 minutes, and is the following. How do we draw random numbers from an arbitrary distribution? Is any of you familiar with random number generators? Okay. Well, one standard property of many programming codes is, at least the most advanced, like Python, they all have a function that allows you to draw random numbers. It's actually a pseudo number generator. And built in, it will have the ability to draw numbers from a flat distribution or from a Gaussian distribution, maybe for a few others. But in general, if you have a distribution that's not even analytical, how do we draw random numbers from that distribution? One way is to do the following. Right. So we have our distribution. So I really don't like these double bumps. We have our distribution. And for simplicity, let's assume it's bound between A and B. And yeah, so we want to draw numbers in such a way that the probability of drawing a number here in this interval, d theta, is yes?
Excuse me. You've been saying the probability to draw a number. What do you mean by draw?
To pick from.
Ah, okay.
So here we're talking about
okay.
Yeah, generating random numbers from a simulation. So
No, I just didn't
Yeah.
understand the word to draw.
No, that's right. It doesn't mean to to draw in that sense. Yeah.
That's what was confusing me.
Okay. Thanks for asking. Yeah, appreciate it. So, right, we want to draw numbers with the probability that's proportional to the area, to this area here. So probability of having numbers between theta and theta plus d theta must be proportional to the area. Now, so we can, I'm going to point out that if we consider the cumulative distribution function, which is defined as the integral of the distribution function from the lower bound to a point theta. Well, and then if I differentiate that, that is d theta p of theta. So, right, I just took the differential of this. Now this is also another thing to point out, that this is the value of CDF for theta when you calculate the integral between A and B, since the probability is normalized, this is 1. But anyway, so this is what we want. This is the area of this rectangle. We want the probability of drawing a value here to be proportional to that. So what we can do is to, and let me just show you. Oops. This is the CDF. So if we draw uniformly, we can draw a uniform. You can draw a value, a random value from a uniform distribution in this quantity, and then we can map it back. So this is a poor attempt at visualizing the process. So we draw t from a uniform distribution between 0 and 1. We take a random number here, and then we go here, and then we go back here. And I guess maybe you can see that the area here is proportional to the space down here, which is another way of saying this, that an infinitesimal in this quantity is equal to p to the integral to the area under this curve. So I'm gonna leave you the lunch break to think about this, and I'll try explain that again better this afternoon before we start with the lab. Are there any questions? So let me first finish. How do you do it in practice? You draw t, and then you set you find the value for which the cumulative distribution function is equal to t, and then you invert this. So in practice, when you're at the computer, what you have to do is to integrate this distribution, which might not be analytic. So, for instance, integrate this, and then use a random number generator to draw a a number between 0 and 1, and then invert this, which might also be not be analytic. So you might have to use some numerical tool to invert this function, but yeah. All right, if there are no questions, I'll see you later.